Welcome to Conceptual Physics at Delaware Tech, Chapter 1, About Science. So in this unit, we're going to talk about what science is, what scientific measurements are and why they're important, the mathematics of science, that's the language of science, the scientific method, and while it says scientific method, the reason why the S is in there is there are multiple scientific methods. We'll talk about the attitude of scientists and people who study science. We'll talk about a little bit about the differences, the similarities and differences of science, art, and religion. And we'll talk about science versus technology. And then finally, how physics is considered the basic science that other sciences are based on. So science is a body of knowledge. In fact, it comes from the word scientia. It's a Latin word that means knowledge. It comes from sciere, which means to know. So science are facts and documents and literature, but it's also an ongoing human activity. Science, some people will say science is a verb because it's really the performance of the scientific method to learn new ideas, learn new facts about the world, about the universe. We're naturally curious. We tend to take things apart throughout our history. People want to know what things are made of, how they work. And they do that through observation and experimentation. And this is part of the scientific method. So it's a systematic study. It's a study of structure around the world, structure of organisms, structure of non-living things, and how they behave in different environments. So both the physical and the natural world. And it's a field that's been around for a long time, since the beginning of since the beginning of recorded history, and even before recorded history, as earlier, probably earlier than 3,000 years BCE. People have been looking at mathematics, astronomy, as well as astrology, but that's not a science, metallurgy, and medicine for a very, very long time, and they've learned to communicate about these fields ever since recorded history. So one of the ways we use to quantify scientific measurements is the use of measurements with specific units in a quantitative way. I'll just read the highlighted parts of this quote from Lord Kelvin. This is where we get the Kelvin temperature scale from. He said, in a physical sense, the first essential step of learning any subject is to find practical methods for measuring some quantity connected with it. When you can measure what you are speaking about, you know something about it. And measurements should be not just descriptive, in other words, they should explain what specifically you're measuring and in what unit, and if it has a direction, you say a direction. But also be quantitative. It's very important that measurements are quantitative as opposed to qualitative, because you want them to be reproducible by others. If somebody said, "What's the temperature outside?" and you said, "Oh, it's pretty warm out." Nobody knows exactly what that means, but if you gave a specific temperature, oh, it's 80 degrees Fahrenheit or it's 37 degrees Celsius, you know what that temperature is, and you could reproduce it in a laboratory. So one of the earliest scientists in recorded history was Eratosthenes, and Eratosthenes lived in the world of ancient Greece. He actually lived in areas outside of Greece itself, but part of the Greek Empire. And he was interested in determining the circumference of the Earth, which is interesting because a lot of people learn that Middle Ages folks thought that the Earth was flat, and this really didn't happen very often. People knew it was round for a very, very long time. And Eratosthenes knew it was round back in 240 BCE. And what he did was he noticed the angles of shadows in two different cities, in Alexandria, which is now part of Egypt, and Syene, which is a little further south of that, close to the equator. And what he noticed is that by looking at the angles of the shadows, he was able to determine that the difference between those two cities on the globe that is Earth is 1/50th of the circumference of a circle. So he knew the distance between the cities and was able to figure that the distance between the cities is 1/50th of the distance all the way around the Earth. That worked out to their units of 252,000 stadia. Stadium was the unit they used. but that's equivalent to about close to 40,000 kilometers or 25,000 miles. And in fact, his measurement was only off by less than 3% of the modern known number for the circumference of the Earth. So this is really astounding technology and science being used to figure out something very fundamental about planet Earth. Another great scientist around the same period, Aristarchus. Aristarchus measured the diameter of the moon, and he actually was interested in a lot of things. He was looking at the distance between the Earth and the moon, the distance between the Earth and the sun. He actually postulated, he didn't have evidence, but he postulated that the sun was the center of the solar system back when nobody believed that. And in fact, that was the belief was that the Earth was the center of the solar system for a couple thousand years until Copernicus's time in the 1500s. So Aristarchus was way ahead of his time, and he was interested in figuring out the size of the moon. Well, what he noticed was that during a solar eclipse, so in a solar eclipse, the moon is between the Earth and the sun. So the moon's shadow hits the Earth. And he looked at the size of that of the moon in relationship to the size of the shadow, which was almost nothing. It was a very small shadow. And then he compared that to the size of the shadow that the Earth casts on the moon during a lunar eclipse. So in a lunar eclipse, the Earth is between the sun and the moon. And he noticed that the shadow was 2.5 times wider than the width of the moon. And by adding one Earth width, using geometry, determined you need to add one Earth width to that, he realized that the Earth, not the shadow, the Earth was 3.5 times wider than the moon. And knowing how wide the Earth was already from Aristophanes' work, he was able to figure out the size of the moon. And in fact, his measurements were less than 5% off from the correct answer. So again, an astounding measurement for its time. So there are a lot of measurements you can do, and they relate to how much you know about something. And one way you could actually do on your own, if you want, is create a pinhole camera. Pinhole camera is essentially just a box or even a piece of cardboard with a small pinhole in it, a tiny little hole. You don't want a big hole, very, very small. And you let sunlight come through that hole. And what will happen is, if you look at this diagram, the sun rays from the left side of the sun and the sun rays from the right side of the sun will be traveling and will come through that hole. Now, the sun's rays go in all directions, but the ones that are pointed in the right direction, both of them, that side of the sun's rays will go into the hole, and they come through, and they'll cross each other at the hole, and they'll come out the other side and form an image of the sun on the ground. Now, you'll notice there's a triangle between the cardboard with the hole and the sun, and there's a triangle between the cardboard and the hole and the ground. And those triangles are what we call similar triangles, so they have similar ratios of sides and angles. And it turns out that by looking at the height that you're holding the cardboard off the ground, you can measure one length, and then you can look at how wide your image of the sun on the ground is and get another length. And what was found was that the length from the cardboard to the ground was 110 times longer than the width of the picture of the sun on the ground. So that tells you that the other triangle above the cardboard has the same ratio. The distance to the sun is 110 times longer than the width of the sun, the diameter of the sun. And by using that information from similar triangles, you could actually calculate it if you know the distance to the sun. And knowing the distance to the sun is about 150 million kilometers, you can quickly determine that the diameter of the sun is 1.4 million kilometers, 1/110th of that length. And in fact, if you do that, you'll get a measurement that's less than 1% off from the true value for the size of the sun. And you can do this yourself. So here's a picture of Paul Hewitt's wife, Lillian, using trees as her pinhole cameras. The little spaces between the leaves form all kinds of shapes, but the sunlight will come through those spaces in the leaves and form images of the sun. And you'll notice the little little images of the sun, they're circular on the ground. It's a little hard to see this because you're looking at an angle, but they're circular images on the ground, no matter what the shape is between the leaves. If you had a pinhole camera that had a square or a triangle or an oblong shape, it'll always be a circle on the ground as long as you're looking flat on the ground. And one way we know that is during a solar eclipse, a partial solar eclipse, when you can still see part of the sun, a crescent of the sun, you will see those pinhole images become crescents on the ground as the light is coming through the trees. And it's a beautiful way of using nature as your pinhole cameras. So it doesn't matter what the shape is between the holes. So mathematics is something that's very important in sciences, and we'll be using some mathematics. We'll be using more proportions than formulas, but there'll be plenty of formulas in the course, and you'll be using your formula sheets as a reference for that, both for the formulas and the proportionalities. But the use of mathematics integrated with science really started in full bloom 4 centuries ago, but as I've already pointed out, it really started happening 24 centuries ago. And the ideas of science are unambiguous when they're expressed in mathematical terms. If you give a number and a unit, there's no arguing about what that number and unit mean. If I say 1 meter, we know exactly what 1 meter is. It's about this wide. We know what 1 kilogram of mass is. We know what 1 newton of force or weight is, and you'll learn about this in this course with the newtons. So it's not like in our everyday use of the English language. Equations of science provide really detailed and factual expressions of concepts in science that can be used to quantitate the properties that we're interested in studying. And these equations, think of them as guides to thinking. And you can actually look at the equations as I discussed in the previous lecture. You can use equations to guide you as to the proportionality of different properties. So there is no one scientific method. There are any number of variations, but I'll show you the general gist of a scientific method. Basically, you want some systematic method of learning new things, and the way that's done typically is you'll observe something about nature, something in the physical world, in the natural world, and you'll notice there's some problem that you don't have an explanation for. And from your observations, you might make an educated guess. We call that a hypothesis. And to be a scientific hypothesis, it has to be a guess that you have the potential for proving wrong. Not right, but wrong. It has to be something where you could come up with a test that, if it gave a certain result, would say it's wrong. If you come up with an educated guess that there's no way to disprove, it's impossible to disprove, that is not a scientific hypothesis. So once you have your hypothesis, you can predict the consequences of other events. And by using that knowledge, you could design experiments that would create certain consequences and allow you to investigate whether that hypothesis really is a good one, whether it matches your data. And typically, the experiment you want to design will either disprove your idea completely, or it will be consistent with your idea. You generally don't get to prove your idea true. You can either prove it false or prove that it might be true. In other words, it's consistent with the hypothesis you had. Occasionally you get something in the middle where the experiment isn't designed as best as you now realize it should be, and you get inconclusive answers somewhere in the middle, and you redesign your experiment and get better answers the next time. But generally the idea is you either disprove it or you're consistent with your hypothesis. And that's what you get from performing the experiments and analyzing the experiments. And then from that, if you have a hypothesis that has passed all your experimental tests and it still holds up and it's never been disproven by any well-designed, well-controlled experiment, at that point you can formulate your theory about what's going on. So your theory has gone past the hypothesis stage, and now it is your best explanation for what's actually going on. It really explains best. And these are considered facts until they're disproven, as long as the theory has been tested very well up until that point. So a hypothesis, just to reiterate, is an educated guess that can be tested, but the hypothesis has to have the capability of being proven wrong. You can't say, oh, my hypothesis is this is magic. Well, there's no way to prove that wrong. It has to be something you could say, oh, my car is run by hamsters turning a wheel inside the under the hood of my car. And you could test that by looking. Are there no hamsters? Well, that proves it wrong. If you see hamsters, that's consistent, but you still don't know if the hamsters are the reason why your engine is working and why your car is moving. So you can see how you can come up with examples on your own about how you can come up with a hypothesis that you can prove wrong, but you can't always prove true, but you can show it's consistent with what you believe. So it's not assumed to be factual until it's supported by experimentation. Hypotheses are never considered to be a fact until they're beaten into the ground with experiments, and at that point we start calling them scientific theories. And scientific theory is your synthesis, your putting together of a large body of information that really encompasses all the great testing that you did and the verification you did of your hypothesis or hypotheses about certain aspects of the natural and physical world. And once you have that scientific theory, in general, not always, but in general, that's considered the best explanation, at least for now, about how or why something works. Now, you might have multiple theories that all are consistent with the data, and we still don't know which one is the correct answer, and that's fine. That happens all the time, especially in physics, and that's fine. Those are accepted scientific theories. We might not know exactly which one's the best, but if there's one good theory, that is considered to be fact until it's disproven by some new, well-conceived, well-performed, well-designed, well-controlled experiment. And examples of this would be natural selection that's a theory about why evolution works. We know evolution is a fact. That's actually fact. There is no question about the existence of evolution. What the theory is explaining how evolution works, and natural selection is our best explanation of that. We know that the universe is expanding. We can actually observe that by looking in telescopes at distant galaxies. We can see them moving faster. And the best explanation for that expansion is the Big Bang. Just to be clear, the Big Bang doesn't explain how the universe started. It explains what happened immediately after it was started and expanded out to fill what is currently the universe. And then general relativity is a theory that was originally proposed by Albert Einstein to explain how gravity works. And we'll talk a little bit about that later on in the semester. So here's a general pathway for a scientific method, but there are variations. You make observations. What did you notice? You ask the question. What does this lead you to ask? How did something work? I saw this happen. How does it work? You come up with an idea of how it works, some testable, educated guess, your hypothesis, your scientific hypothesis. You then design experiments that will test that hypothesis. The experiment, in theory, should give you an answer that says the hypothesis is just wrong, or it might be right. It's consistent with my hypothesis. And you keep doing more experiments. You don't just do one experiment that shows it. You might do dozens or even thousands, or even in the case of evolution and the Big Bang, tens of thousands of experiments that until they're all consistent with your hypothesis, and then it gets elevated to the concept of scientific theory as an explanation of what's happening, and we consider those scientific fact. So you look at your results of your experiments. Did it disprove it, or does it support it? Is it consistent with it? And then you'll do a little further analysis, and from the analysis, you might make more observations, and go around in this loop again. But if you've done it enough times, after a while, you can formulate your theory, as long as it's based on well-tested experiments that are well designed and give conclusive data about what's going on, and then you can really trust that experimental that scientific theory. So the scientific attitude is one of inquiry and experimentation. I think that goes without saying. You're asking questions about the world and you're experimenting. But what a lot of people don't realize, it's also a strong willingness to admit when you're wrong. Science doesn't work unless scientists are willing to say, well, my idea, it was an educated guess, but it was just plain wrong. And you have to drop it and go to something else, or maybe you tweak it a little bit. You make it a little bit better, and so that it fits the data, or you just scrap it completely and come up with something completely new. And people do both things all the time. But the idea is, if you have good experiments that consistently, reproducibly disprove your hypothesis, you got to accept that it's wrong and come up with something else or some new explanation. So scientists have to accept their experimental findings, assuming they've designed the experiments well and they've done all the proper controls and everything was analyzed properly, because mistakes do happen on occasion. But when you have lots of people looking at your experimental designs and nobody can find any mistakes, and lots of people have done experiments of all kinds, and you all come to the same conclusion, after a while you build up a lot of confidence that your theory is correct. So scientists have to be an expert at changing their minds. I've actually had scientific theories in the work that I've done in the past, and I was wrong, and we had to reformulate the theory for what was going on to explain any new data in our findings. We have to follow with the data. That is the way science works. If it tells us something's wrong, it's not always easy, but we have to do it. We have to say, okay, that was wrong. It's not my fault it was wrong. That's Mother Nature playing games with us, and that's happened to me on more than one occasion. And then you learn something new, and you're better off for it, and science is better off for it. So science is always changing, but certain things have been really beaten into the ground so well that they're extraordinarily well accepted, like the three examples I gave you earlier. So here's a question for you, and you'll see these kinds of questions throughout the semester. This one's titled The Scientific Attitude, and if you're near other people, you can check your neighbor. If you were in class, you can check your classmate. The question is, which of these is considered a scientific hypothesis? The moon is made of green cheese. Sounds silly, but is it a scientific hypothesis? Atomic nuclei are the smartest particles in nature. A magnet will pick up a copper penny. Cosmic rays cannot penetrate the thickness of your textbook, Conceptual Physics. Which one is a scientific hypothesis? Well, turns out all of them are scientific hypotheses. And usually I'll give you an option of all of the above, but this is the one time I won't be giving you that option. Why are these all scientific hypotheses? Well, even if they're silly, like A is, they're all scientific hypotheses because all of them have potential tests to prove them wrong. What we call proving wrongness or proving or falsifiability. They're all falsifiable. The moon is made of green cheese. If we go to the moon, we find out it's made of other things. It's not green cheese, disproven. Atomic nuclei are the smallest particles in nature. We find one particle smaller than atomic nuclei. That's wrong. A magnet can pick up a copper penny. Take a copper penny, pick it up with a magnet. Try a strong magnet. If nothing picks it up, it's not true. Cosmic rays cannot penetrate. Well, if you have a detector on the other side of the book and you detect cosmic rays, well, then that's wrong. It's been proven wrong. And I'm not saying which ones of these are true or false. The point is they are all falsifiable. They all have the potential to be tested and shown to be wrong. And that's what makes a hypothesis, a guess, a scientific hypothesis, and a real, true, educated guess. Here's another one. Which of these is not a scientific hypothesis? Protons carry an electric charge. Undetectable particles are some of nature's secrets. Charged particles' paths bend when in a magnetic field, or all of the above. I'll give you a second to think about that. And we look, it's undetectable particles are some of nature's secrets. Because A and C, there are experiments that could prove them false if they are false. Protons do, of course, carry a positive charge, an electric charge, but you could potentially prove that that was false through various experiments. Uncharged particles, C, their paths bend in a magnetic field. Well, if you have them, you shoot a beam of charged particles past a magnet, does the path bend? If it doesn't bend, Well, that would disprove it, and I'll tell you they do bend. Charged particles will bend either towards the magnetic field or away, depending on the charge and depending on the magnetic field. So B has no test for wrongness. Undetectable particles are some of nature's secrets. What does that even mean? How could I possibly disprove that? So we have other terms besides hypothesis and theory. We also have scientific law or principle. And this is a concise scientific statement of fact. Sometimes this is confused with theory, and sometimes it overlaps with theory, but it's a hypothesis that's been tested repeatedly, like a theory has, and has never been contradicted by credible experimentation, like a theory has, and explains what happens, like a theory has, but it's frequently in the mathematical formula form. So these are often parts of theories. They're usually mathematical predictions for how things behave. They don't always explain why they behave as in a theory. So that's the big distinction. These show you how it happens in as far as the relationship. So the law, look at the first one, E equals mc squared. This shows you the relationship between mass, m, and energy, E. Energy that is released from mass that's converted to energy is equal to that amount of mass times the speed of light squared, which is a gigantic number. So a tiny amount of mass can be turned into an enormous amount of energy if you could do that. So that's a mathematical relationship. It doesn't tell you why it happens. It tells you mathematically what the relationship is, that the mass is proportional to the energy is proportional to the mass, and the energy is also proportional to the speed of light squared. And you could do that with each of these others, and we already did the last example in the previous presentation. So a scientific fact is a close agreement by competent observers, so this means it's really been looked at in detail, based on repeatable and reproducible observations. So lots of different experiments done over and over again to prove with measurements, with quantitative measurements, that something is what you believe it is. And the goal is for scientific facts to be truth. On a rare occasion, they turn out to not be truth. A mistake is made, something new is learned. So they are revisable in this definition of fact. I have a slightly different definition of fact, but I'm going to use the definition that the author of the book provides, saying that facts are revisable pieces of data, and therefore the goal is to be the truth, but it might have to be revised at some later date when new information is discovered. So the Earth is round. It's nearly spherical. It's just slightly off from spherical because of the rotation of the Earth. So that's a fact. The evolution of species, that's a fact. It's not a theory. That's actually a scientific fact. The explanation for it is the theory of natural selection. But the evolution of species has actually been observed even in modern day. So we know that's a fact. So which of these often changes over time with further study? Facts, theories, both, or neither? Well, I think I've said that both will change according to the definition that the author uses for facts. They can be revised. Theories certainly are revised when new information might be found that isn't consistent with the previous theory, and it has to be tweaked or completely discarded and a new theory arrived at. So both can change, and this is really the hallmark of good scientific method. It's the hallmark of a good scientist who's willing to accept the fact that these things can change over time. A person who says that's only a theory, and I know you've heard this, likely doesn't know that a scientific theory is A, guess, B, number of facts, C, hypothesis of sorts, D, vast synthesis of well-tested hypotheses and facts. Well, as it turns out, I already highlighted the answer for you. I'll have to fix that. But yes, it is a vast synthesis of well-tested hypotheses and facts. A theory is not a guess. And even a hypothesis is not just any guess. It's a educated guess that can be testable as possibly being false. A number of facts, that's just a collection of facts. It doesn't necessarily explain things. So the word theory in everyday English usually is used the same way as a hypothesis, but in science we use theory to mean something very different. That it's really a vast experimentally verifiable body of knowledge that's been elevated to the level of being called a scientific theory. It's our best explanation of what's going on. So, science, art, and religion. There are people that are passionate about science, about art, about religion. Some people passionate about two of these or all three of these. And I'm passionate about the understanding of all three of these. But the search for order and meaning in the world around us has taken different forms. I think this is a quote from the book. So what does this mean? Well, it means that art, science, and religion are all domains of study that people are very passionate about, and that's perfectly good. That's great that they're passionate about, but they don't necessarily conflict with one another because they really occupy explanations of different aspects of the universe around them. Science is the natural is of the natural order, and it involves the discovery and recording of natural phenomena, and it has to be testable. If it's not testable, it's not considered science. Art, on the other hand, is a personal interpretation and expression of human experience, sometimes animal experience. If you've ever read about people that use elephants or chimpanzees or sugar gliders to do paintings as well, but art is a personal interpretation. It's a personal expression. And religion involves faith, and faith, obviously, by definition, is believing things that there might not be evidence for, but that's your faith, whereas science absolutely requires evidence to postulate a theory explaining what is going on around them. They can't take anything on faith. And religion frequently involves the worship of one or more supreme supernatural or spiritual beings, whereas that's usually not part of the study of science. There are plenty of scientists who are quite religious, and throughout history, most scientists were extremely religious. That may be changing more in modern times, but they don't have to conflict with one another. They occupy explanations of different domains of the universe. So there are similarities between these fields as well as differences. Between art and science, knowledge of what is possible in the human experience and in nature, that's common to both of those. Knowledge of both aspects of our views and decisions about the world is influenced by art and science. And you could really argue that for some people, religion holds a part in that as well. As far as religion and science, the similarities both deal with unanswered questions. The approach is completely different, but they both seek to answer questions about the universe that they'd like to know the answers to. So, question for you. Between a pilot and a priest, who do you think should fly a commercial airplane? Who should perform a marriage? And of course, these questions are no-brainers, but they have a point. I know this is very silly. So A pilot should fly and a priest should perform the marriage. B, the other way around. C, the pilot should do both. D, the priest should do both. Well, I think it's pretty obvious. The pilot should do the flying and the priest should perform the marriage. They have different skills for different tasks. They're in different domains of human experience, and each can do their own thing very, very well. Now, as far as science and technology, science is concerned with the gathering and organizing of knowledge. It's concerned with gathering information, observing, coming up with ideas about what's going on, testing those ideas, those hypotheses, formulating theories that are consistent with all the observations from experiments, and really coming up with an idea to explain what they see in the universe. Whereas technology is using that knowledge, using that scientific knowledge that's already been gained about how things work, and coming up with practical uses for it, and providing tools for further experimentation. So the most obvious use of technology is by engineers, mechanical engineers, electrical engineers, material scientists, engineers. There are lots of different engineering fields that take advantage of the science knowledge. Sometimes they'll add to the science knowledge, so there is an overlap between people that work in one or the other field. A lot of people work in a combination of the two, but they generally are different realms of using that information. One group is collecting and determining what that information, those explanations are, and one is finding practical uses to help the world, hopefully help the world. So the physical sciences are what we refer to as the ones that are not directly related to living organisms. Those are geology, though geology sometimes has living organism components, especially when you're looking at fossils. Astronomy, chemistry, and physics. And of course, there are chemistry of biological systems, but that would be considered more of a life science. So biology as well as biochemistry, zoology, anatomy, physiology, botany, study of plants, and medicine. These are all life sciences. But what they have in common is physics is fundamentally the basis of all of these. How matter interacts with matter, how energy interacts with matter, how energy interacts with energy, that's the domain of physics. And that is the underpinning for studying larger things like atoms and molecules in chemistry, or larger molecules still in biochemistry, which leads you to how how biology works. And that's part of zoology and anatomy and physiology and botany and medicine. They all stem from those fields. So you can think of sciences as a pyramid where physics is the basis for everything. And from physics, we can base what we understand about chemistry based on the concepts of physics. We can base biology on the biochemistry and chemistry. We can base physiology, how the reactions of our body and the behavior of our body, on the biology. Sociology, our general human behavior or animal behavior, if you're studying animals, is based on that. And in turn, the arts are kind of the pinnacle of expression by humans. So you have this pyramid, and you might even argue that mathematics is the underpinning of physics. So sometimes you'll see mathematics at the bottom of this pyramid as well, because in many ways physics is dependent on the mathematics, but it really uses mathematics as a tool to help predict what happens in physics. It's not necessarily the explanation of why something's happening in physics. So we think of physics as the foundation. So this question is, although physics may be the most difficult science course in certain schools, when compared with the fields of chemistry, biology, geology, and astronomy, in terms of scientific complexity, physics is A, the simplest, B, still the most complex, C, the central science between chemistry and biology, and D, simple enough, but only for especially intelligent people. Well, I know this may not seem obvious to you at this point, but the fact is, in terms of scientific complexity, it's actually the simplest. If you think about the physics itself, physics has fewer terms than biology and chemistry. There's a lot of nuance in chemistry. There's far more in biology, even more still in physiology. And the details of why this works, if you were trying to explain some physiological response in your body, you would have to say, oh, that's due to these interactions of the structures in your body. And that's because, so that leads you to the biology. And that biology is based on the biochemical reactions. So it's the chemistry of the biology of the molecules in your body. And then the chemistry of the molecules in your body, well, their behavior is based on the physics of the atoms and the molecules and the subatomic particles. And that's that's in turn based on the fundamental forces of physics. So you can go back in time, back in complexity to the quote unquote simplest science, physics. We know it's not simple to take in classes, but in terms of the complexity of explaining something, it's much easier to explain something in physics than say in physiology, where you may have many factors involved in explaining why a certain phenomenon happens in a living body or a living piece of tissue. So physics is on this basis is considered the more basic of the scientific fields. And with this, we'll end chapter 1. Thank you very much.